Today I want to discuss chapter 9, which talks about search and sort. We can say an algorithm is a sequence of steps for accomplishing a task. Whenever we take some steps to complete a task, we can say that is an algorithm. We have many algorithms. One of them is linear search. In linear search, we say linear search is a search algorithm that starts from the beginning of a list and checks each element until the search key is found or end of the list is reached. In this example here, we're searching for key 14. So in linear search, we start from the first one. We keep looking until we could find it. So if we start from the first one, is 14 equal to 6? No. Is 14 equal to 24? No. Is 14 equal to 16? No. When we get to the index 3, we find 14. So search key is found at index 3. In linear search, we look one by one until we find it. This is the linear search algorithm. You can see that we have this linear search function, which the return type is integer. It takes an array of integers. It takes numbers size, which is an integer, and key, which is another integer. We define integer I. We start from the first one, index 0. We keep going until last one, which that is number size minus 1. We compare each element in the array with the key. If that element is equal to key, we return I. In this example, you can see that the linear search looks one by one until it finds that element inside the array. If it couldn't find it, then we say we couldn't find it, and it returns minus 1. We define an array of some integers. We define a unconstant integer number size, which is h. So this for loop will display the array. This is how we can call the linear search. We say linear search numbers size key. So when we pass this number is an array of integer. We're passing it to the linear search function. We pass the size of that array and we pass the key. When we make this call, this linear search function runs. If it does find that element in the array, it returns the index. If it couldn't find that element in the array, it returns minus 1. If the key index is equal to minus 1, it means that that element was not found. It displays key was not found. Otherwise, it displays the key was found at specific index. We could say an algorithm runtime is the time algorithm takes to execute. Different algorithms, they have different runtimes. For example, if each comparison takes 1 microsecond, a linear search algorithm runtime is up to 1 second to search a list of 1 million elements, 10 seconds for 10 million elements, and so on. In linear search, we start from the first one. We look one by one until we find it. If we couldn't find it, then we return minus 1. So we could say a linear search is a very slow algorithm. For example, if you want to search Amazon online store, it has more than 200 million items, it could require more than 3 minutes. So when we talk about how long it takes for algorithm to run, we could use the runtime complexity and runtime to see, we can use the runtime to see how long it takes for that algorithm to run that program. So an algorithm typically uses a number of steps proportional to the size of the input. For a list of 32 elements, linear search requires at most 32 comparisons. One comparison if the search key is found at index 0, 2 if the found at 1, and so on to 32 comparisons if the search key is not found. So you can see that using linear search, If we have 32 elements, the maximum or the worst case scenario is 32 compares. If the element that we're looking for is the first one, if it's index 0, only one compare will give you the result. If it's not the first one, then we keep looking for it until we find it. If we couldn't find it, return -1. But the worst case scenario is if that element doesn't exist inside that array, which means we have to look at every element inside the array and then we couldn't find. So when we talk about the time complexity, sometimes we have best case scenario. Sometimes we have average case scenario. Sometimes we have worst case scenario. If you look at the binary search, we can see binary search is faster for searching a list if the list elements are sorted and directly accessible, like array. So for the binary search to work, the array that we're sorting, it has to be listed. It has to be sorted. So in order for the binary search to work, we have to first sort that array. In this example here, we're looking for search key 16. We have 2, 5, 6, 14, 16, 24, 32, and 63. You can see the elements are sorted. So we start this search by checking the middle element. 0 plus 7 divided by 3, the 0 plus 7 divided by 2, it gives us 3. The middle element index is 3. We have the key, the search key is 16. 16 is not equal to 14, but 16 is greater than 14. We change the low to 4, high to 7. 4 plus 7 divided by 2, it gives us the mid 5. So when we change here, low to the 4, high to 63 or index 7, we're looking for 16. 16 is not equal to 24, but 16 is less than 24. Since 16 is less than 24, we change the low and high, and then we look at the element 4, which it contains the 16. The search key is found at index 4. So in order to understand the binary search, first we look at the middle one. If it's the middle one, we found it. If it's not the middle one, is it greater than middle one or less than middle one? If it's greater than the middle one, then we look at the right side. If it's less than the middle one, then we look at the left side. And then we keep doing this until we find it. If we couldn't find it, we return -1. We call this binary search because every time we divide the elements by half. This is the C++ function for binary search. We have an array of integers. We have number size and key. So we find the high, which is number size -1. We say the low is equal to 0. We say while high is greater equal to low, we find the middle one. If the key is greater than the middle one, we change the low to mid +1. Else, if the key is less than the middle one, we change the high to mid -1, and we return the mid. So this code here, you can see that we're changing the low and we're changing the high. It means by comparing the value of the key to the element that is the middle element in the array, we keep changing low and high until we find that element. If we couldn't find it, we return -1. If we want to call the binary search, we define an array of integers. So we call the binary search, we pass the array, we pass the size, and we pass the key. If the key index is equal to -1, we say and we display key was not found. Otherwise, we display the key was found at specific index. So we have something we call an O notation, big O notation. Big O notation is a way of describing how a function, runtime of an algorithm, generally behaves in relation to the input size. So in this example, we have an algorithm that is 5 algorithm steps are 5 plus 13 times n plus 7 times n squared. If you want to find the big O notation of this algorithm, we can say the big O notation of 5 plus 13n plus 7 times n squared is O of n squared. Because if you compare these, when the n grows to a large number, 7n squared will grow faster than other terms. If the n becomes a very large number, 7 times n squared is much bigger than 13n. And 13n will be bigger than 5. So the most important term here between these three is 7n squared. We could ignore other ones, and we can say the big O notation of a 5 plus 13n plus 7n squared is the big O notation of 7n squared, which is big O notation of n squared. We say this is O of n squared. There are some rules here. We say if f of x is sum of several terms, the highest order term is kept and others are discarded. The highest term is 7n squared. If f of x has a term that is the product of several factors, all constants are omitted. So whenever we have product of several factors, we could ignore the constants. In this example, we're ignoring this 5. So we have some rules for determining big O notation of composite functions. C times O of f of x is the big O notation will be O of f of x. C, which is a constant, plus O of f of x. The big O notation is O of f of x. Gx times O of f of x will be O of gx plus fx. Gx plus O of f of x will be O of gx plus fx. These are some rules when you want to determine the big O notation of composite functions. If you look at table 9.31, we have the growth rates for different input size. You can see that different functions, when the n grows, we have different input sizes here. Like when we have this function of log n, when the input size is 10, it takes 3.3 microseconds to run. When the n grows to 50, it's 5.65 microseconds. When the n becomes 100,000, the log n will have a runtime complexity of 16.6 microseconds. You can see that the runtime for n, when the n grows from 10 to 100,000, you can see when we have a logarithmic function, the time to execute will grow from 3.3 microsecond to 16.6 microsecond. If the function is n, and then the input size is 10, we have 10 microseconds. But if the input size is 100,000, this is 0.1 second. When we have n squared, if you look at the n squared, when the n grows, the time to run becomes 2.7 hours, which is a long time comparing to 0.1 microsecond when n is 10. When the n grows from 10 to 100,000, the time to run when the function is n squared grows to 2.7 hours. When we have n to the power of 3, and then the input size is 10, you can see that we have 1 microsecond when the input size is 10. But when the n is 100,000, it's 31.7 years. It means if you solve a problem using time complexity of n to the power of 3, and if the input size is 100,000, it took almost 32 years to solve that problem, which is a very bad case. It takes a very long time to solve a problem. But if you could solve the same problem with an algorithm that the time complexity is n, it takes 0.1 second. The difference between 0.1 second and 32 years when you find a solution that it uses time complexity of n or time complexity of n to the power of 3 is a lot. That is a difference. That is a difference that how you can solve problems. If you look at this graph here, you can see when the number of elements grow, the number of computations increases. If you look at the one, you can see when the number of elements grow, the number of computations is the same, is 1. But if you use a log n algorithm, you can see that the number of computation increases. But if you have n, the number of computation increases faster. And when you have n squared, it grows fast, the number of computations. But if you use an algorithm, which is 2 to the power of n, it still grows. If you have n factorial, this graph shows how the number of elements can increase the number of computations using different algorithms. This figure 9.3.2 discusses the runtime complexity for various pseudocode examples. In this example, we have a function. It has only one single if statement. If this condition is true, return this. Otherwise, return that. The big O notation of this function is 1. Why? Because either this runs or this runs. If this condition is true, this runs. If this condition is false, this runs. There's only one. There is only one step involved here to solve this problem. Because if this condition is true, returns X, otherwise it returns Y. If you look at the binary search, you can see that the binary search takes an array, N, and key. The time complexity of binary search is O of log N. So it's logarithmic. Why? Because binary search every time will divide the elements into the half. And then if it's the middle one, it finds it. If it's not the middle one, it keeps looking at it. This is log n base 2. So whenever you break a problem in every time into the half, and then you keep breaking those halves into the halves and halves and halves, we can say the time complexity of that algorithm is log n base 2. If you look at the linear search, you can see that the linear search takes numbers n and key. We have a for loop here that goes from 0 to n. We compare nums I and key. If the numbers I is equal to key, we return I. This is O of n. Why? Because this for loop goes from 0, it starts from 0, it goes to the n, and then it adds 1 by 1. In the worst case scenario, this for loop will happen n times. Since in the worst case scenario it happens n times, this is O of n. We say the time complexity of linear search is O of n. If you look at the merge sort takes these numbers. It calls the merge sort on numbers I and j to sort the left one. And then it calls the merge sort for on numbers j plus I and k to sort the right side. And then it will merge numbers I, j, and k. It will merge those parts. It's O of n log n base 2. Because if you see here, you're breaking down the problem into the solving the left side and right side. It means you're breaking the problem into 2 different parts, which is left side and the right side. But then you have to merge them. So the total algorithm will have a time complexity of n log n. If you look at the selection sort, you can see that the selection sort is O of n to the power of 2. Because we have a for loop here that goes from 0 to n, and then we do have another for loop that goes from I plus 1 to n. We have one for loop inside another for loop, which each one is iterating at max n times. We can say this is O of n squared, which that is the worst case scenario, which is n to the power of 2. So we could say the time complexity of selection sort is O of n squared. And if you look at the Fibonacci series, it's O of c to the power of n. If this condition is true, it returns 1. Otherwise, it will return the Fibonacci of n minus 1 and Fibonacci of n minus 2. We could say the Fibonacci series is O of c to the power of n, where c is a constant. So you can see that we have this for loop that I becomes 0. We have I less than n plus I. One operation is here. One operation is I equal to 0. And then we have n iterations. If we add everything together, we have n iterations here. We have 2 operations here. And then 2 operations happen in the worst case. So we have one final operation. We can add everything together. 1 plus 1 plus 1 plus n times 2 plus 2, which is 3 plus 4 times n. This is O of n. This algorithm, the runtime complexity of n. So when you have a for loop that goes from 0 to n, the time complexity of that for loop is O of n. Because in the worst case scenario, it will iterate n times. Maximum number of times that these statements they can run is n. We say the function f of n specifies the number of operations executed for input size n. So the time complexity of this algorithm is O of n. If you look at this example here, we have a for loop. This for loop starts from 0, it goes to the n. Inside the for loop, we have some statements. On top of the for loop, we have one statement. Under the for loop, we have one statement. So these are statements that are O of 1. Sum equal to 0, that is O of 1. This statement here is O of 1. We could omit the constants in big O notation. So if you look at this algorithm, we have n iterations in this for loop. This is O of 1 plus n times O of 1 plus O of 1, which is this is O of n. So whenever you have a for loop that iterates n times, that for loop is O of n. We say the sorting is the process of converting a list of elements into ascending or descending order. When we put some elements either into ascending, for example, given a list of numbers, 17, 3, 44, 6, and 9. After sorting, the list becomes a 3, 6, 9, 17, and 44. We say the list is sorted. We could sort elements either in alphabetic order, or we can arrange them into to have ascending zip codes. So sometimes we have some numbers that we can sort them from smallest one to the largest. Or we can sort them from the largest one to the smallest. Sometimes we have some characters that we want to sort them in order. So the question is how we could sort some elements. One of the algorithms that we use to sort is called selection sort. We say selection sort is a sorting algorithm that treats the input as 2 parts. a sorted part and an unsorted part, and repeatedly selects the proper next value to move from unsorted part to end of the sorted part. Let's look at this example to understand selection sort. We have 7, 9, 13, 18, and 8. We have all of these elements are white. It means they're not sorted. We have I and we have J. So in selection sort algorithm, selection sort treats input as two parts, a sorted part and unsorted part. Variables I and J keep of track of two parts. The selection sort algorithm searches the unsorted part of array for smallest element. Index smallest stores the index of the smallest element found. We look for the smallest element, which is 3. Index smallest is pointing to element at index 2, which it contains 3. Elements at I and index smallest are swapped. We swap those two elements. 3 goes here and 7 goes there. Indices for the sorted and unsorted part are updated. We have a sorted part which contains 3. We look for the smallest index, the smallest element in the unsorted part. We swap that smallest element with element at I. The process is repeated until all elements are sorted. If we keep doing this, you can see that everything gets sorted. So in selection sort, we select the smallest element. We swap it with the first one, and then that one is sorted. We keep looking for the next smallest one. We swap it with the second one. Then we keep looking for the next smallest one until everything is sorted. This is the selection sort algorithm, which takes an array and it takes number size. You can see we have the index of smallest here. We have a for loop that starts from I to number size -1. We find the index of the smallest one. We go from I plus 1 to number size. We keep comparing the numbers index smallest and numbers J. And then we keep a track of index smallest. This code here does what I explained. It looks for the smallest one. It uses a temp variable to store numbers I, and then it swaps that smallest one with the first one, and then the second one, and the third one, and then it keeps doing it until everything is sorted. So we define an array, and then when we call the selection sort, it takes this array and number size, and it sorts the array. We say selection sort may require a large number of comparisons. The selection sort algorithm runtime is O of n squared. If list has n elements, the outer loop executes n-1 time. For each of those n-1 outer loop execution, the inner loop executes on average n divided by 2 times. We can say the total number of comparisons is proportional to n-1 times n divided by 2, which is O of n squared, which is a very slow algorithm. Selection sort is very slow, especially if the n grows. The selection sort will take a long time to execute. We have some other sorting algorithms that involve more complex algorithms, but they have faster execution times. We have another sorting algorithm that we call it insertion sort. We say an insertion sort is a sorting algorithm that treats the input as two parts, a sorted part and an unsorted part, and repeatedly inserts the next value from the unsorted part into the correct location in the sorted part. In this example here, insertion sort treats the input as two parts, a sorted and unsorted part. The sorted part is white. The sorted part is gray. The unsorted part is white. Variable I is the index of the first unsorted element. Initially, the element at index 0 is assumed to be sorted, so I start at 1. So in this example, you can see that variable j keeps track of index of the current element being inserted into the sorted part. If the current element is less than the element to the left, the values are swapped. Once the current element is inserted in the correct location in the sorted part, I is incremented to the next element in the unsorted part. If the current element being inserted is smaller than all elements in the sorted part, that element will be repeatedly swapped with each sorted element until index 0 is reached. So if you pay attention here, in insertion sort, we have two different parts, sorted part and unsorted part. We keep comparing 32 and 6. Since a 6 is less than 32, we insert 6 there. So we have 6, 32, 15, 3, and 20. We compare 32 and 15. Since a 32 is greater than 15, we insert 15 before 32. Since 15 is less than 6, we swap them. We have 6, 15, 32. We compare 32 and 3. 32 is greater than 3. We compare 3 and 15. 3 is less than 15. We swap them. We insert 3 before 15. 6 is greater than 3. We insert 3 before 6. Thirty-two is greater than 20. We inserted 20 before 32. 15 is less than 20. We don't need to swap them. Everything is sorted. This is the C++ function for insertion sort. We can say the runtime complexity of insertion sort is O of n to the power of 2, is n squared. If a list has n elements, the outer loop executes n minus 1 times. For each outer loop execution, the inner loop will need to examine all elements in the sorted part. Thus, the inner loop executes on average n divided by 2 times. The total number of comparisons is proportional to n minus 1 times n divided by 2, which is O of n squared, which it means slope. So if the n grows, n squared grows fast. We can say this is a slow algorithm. We have also quicksort, which quicksort is a sorting algorithm that repeatedly partitions the input into low and high partitions, and then recursively sorts each of those partitions. We have a pivot, which pivot can be any value within the array being sorted, commonly the value of the middle array element. It can be anything inside the array. In this example here, the pivot value is the value of the middle element, which the middle one is 6, index 2. We partition the elements into two different parts. This partition functions, let's see how it works. The pivot value is the value of the middle element. Index I begins at element I and is incremented until a value greater than pivot is found. Index H begins at element K. It is decremented until a value less than the pivot is found. Elements at indices I and H are swapped, moving those elements to correct positions. The partition process repeats until indices L and H reach or pass each other, which is L greater or equal to H, indicating all elements have been partitioned. Once partitions, the algorithm returns H, indicating the highest index of the low partition. The partitions are not yet sorted. So in this example here, you can see that we start with pivot, which pivot is the middle element. So the midpoint element is 6. When we finish partitioning, 6 and anything less than 6 is in the low partition. Anything greater than the 6 is in the high partition. We have two different partitions. Low partition includes a 6 and 4. High partitions includes a 7, 18, and 8. This is the quicksort function. It takes numbers and I and k. So this example, it shows how we divide these elements into two different partitions. One of them is 6, 4. One of them is 7, 18, and 8. And then the pivot here for 6 and 4 will be 6. We get two other partitions, 4 and 6. Once we reach to one element, that array is sorted. 7, 18, and 8, the pivot is 18. We get two partitions, 7 and 8 and 18. For 7 and 8, the pivot will be 7. We get two different elements, 7 and 8. 18, when we reach one element, everything is sorted. We get 4, 6, 7, 8, and 18. Low partition contains one element, so partition is already sorted. High partition contains one element, so partition is already sorted. All elements are sorted. We put them together, folks, 4, 6, 7, 8, and 18. This shows how quicksort works by partitioning based on pivot. This is the quicksort algorithm, which takes an array of integers that takes I and k. It does the same thing I explained using this partition function. So let's take a look at merge sort. But before that, we can see the quicksort runtime is O of n log n. Quicksort has several partitioning levels. The first level dividing the input into 2 parts. The second into 4 parts. The third into 8 parts. At each level, the algorithm does at most n comparisons moving L and H indices. If the pivot yields 2 equal sized partitions, there will be log n levels requiring the n times log n comparisons, which is a fast algorithm. We call it quicksort because it's quick. It's faster than n to the power of 2. N log n is much faster than O of n squared. We have also merge sort, which we say merge sort is a sorting algorithm that divides the list into 2 halves. Recursively sorts each half and then merges the source halves to produce a sorted list. The recursive partitioning continues until a list of one element is reached, as list of one element is always sorted. Let's take a look at merge sort. We have 3, 11, 8, 18, 4, and 25. Merge sort recursively divides the list into 2 halves. We get 3, 11, 8, we get 18, 4, and 25. 0 plus 5 divided by 2 is 2. The list is divided until a list of one element is found. 0 plus 2 divided by 2 is 1. We get 3 and 11. 0 plus 1 divided by 2 is 0. We get 3 and 11. 8. 3 plus 4 divided by 2 is 3. We get 18. and 4. 25 is only one element. The list of one element is already sorted. We get 3, 11, 8, 18, 4, and 25. At each level, the sorted lists are merged together while maintaining the sorted order. We get 3, 11, and then 8. We put 3, 11, and 8 together, but 8 goes before 11. We put 4 and 18 together. 4 goes before 18. 4, 18, and 25. We get 4, 18, and 25. We merge them together and we get 3, 4, 8, 11, 18, and 25. You can see that merge sort works with merging. We're merging these together. We can say the merge sort merges the two sorted partitions into a single list by repeatedly selecting the smallest element from either the left or right partition and adding that element to a temporary merge list. Once fully merged, the elements in the temporary merge list are copied back to the original list. This is the function, C++ function for merge sort. It does the same thing I explained. We can say the time complexity of the merge sort, the runtime is O of n log n. Merge sort divides the input into half until a list of one element is reached, which requires log n partitioning levels. At each level, the algorithm does about n comparisons, selecting and copying elements from left and right partition, yielding n times log n comparisons. So the time complexity of the merge sort is n times log n base 2, which is fast. It's a fast algorithm. I did talk about some search and sort algorithms. I want you guys to study chapter 9.